Welcome, everyone. This presentation introduces our asset management plan and sets the foundation for how we structured a defensible and transparent decision-making process. First, the purpose of the AMP is to translate strategy into practical actions, ensuring assets continue delivering value to users. Our work aligns with international frameworks such as ISO 55000, the IM, and NMS, which emphasize lifecycle thinking, risk-based planning, and clear levels of service. Because asset decisions must be defendable, especially when budgets are limited, our approach follows a structured methodology, assessing condition, defining performance expectations, and prioritizing interventions based on value and risk. Finally, we use the Alaska Road Network dataset as a simplified real-world model. Although the data is limited, it provides a realistic scenario for building an AMP using engineering logic, lifecycle management, and performance-based planning. This slide summarizes what an asset management plan actually does and the frameworks supporting our methodology. An AMP turns strategy into a practical plan, defining assets, assessing their condition, understanding risks, and determining what resources are required to maintain acceptable levels of service. It covers inventory, deterioration, financial forecasting, intervention planning, and continuous improvement. The goal is transparency, long-term sustainability, and ensuring every dollar spent delivers measurable value. Our approach follows recognized global standards. ISO 55000, which defines asset value, lifecycle optimization, and loss expectations. The IM Anatomy, which outlines the core capabilities required for mature AM. The NMS Manual, widely used for municipal infrastructure planning. And engineering literature such as Haas et al. And Mohammadi and Amador, which guide pavement performance modeling and treatment logic. Together, these frameworks ensure our AMP is not arbitrary. It is structured, evidence-based, and aligned with best international practice.
In this project, we began by reviewing the dataset available for the road network. We confirmed that the dataset contains useful condition indicators such as IRI, cracking, rutting, LOS, and segment length. However, several key engineering fields were missing, including construction year, traffic data, structural number, and material type. We also identified some data quality issues, such as outliers, zeros, and inconsistent LOS scoring. Because of these limitations, the dataset is not suitable for mechanistic or age-based modeling, but it is fully sufficient for LOS-based prioritization, which is the approach used in this asset management plan. To evaluate performance, we grouped the network into three homogeneous categories: highways, local roads, and ramps. LOS was selected as the primary indicator because it is the only composite measure consistently available across all segments, capturing roughness, rutting, and cracking together. We then adopted a simplified exponential deterioration model to describe how LOS declines over time. Finally, we defined treatment triggers based on LOS bands, from good to failed, which allows us to assign the appropriate type of intervention for each segment. Our approach is aligned with lifecycle asset management principles. Preventive maintenance is emphasized because it delivers the highest lifecycle value. Highways and ramps carry higher traffic volumes and therefore have a greater consequence of failure. Segments with LOS below 55 are flagged as high or critical risk. By integrating deterioration, current condition, and risk, we ensure that interventions are applied at the most cost-effective time while maintaining the required level of service.
Our financial planning approach begins with the city's annual budget of $30 million. To allocate this effectively, we distributed funds based on each roadway group's network share and criticality. Highways, being the backbone of regional mobility, receive roughly $22 million, followed by $14 million for local roads and $3.97 million for ramps. Once the budget buckets were set, we applied our CPS-ranked selection model, which prioritizes segments using a weighted score combining IRI, rutting, cracking, and level of service. This ensures funds go first to the highest need and highest risk segments. Finally, LOS-based treatment levels determine how much of each segment's budget is consumed, so higher severity segments naturally trigger higher cost interventions. This aligns the financial plan with both engineering needs and service quality goals. Performance and Improvement Plan. For the improvement plan, we structured actions over 3 time horizons. Short-term, years 1 to 2, we focus on high-risk highways and ramps because these segments carry the greatest traffic volumes and pose the greatest safety and mobility risk if left untreated. Medium-term, years 3-4, once immediate risks are controlled, we address the remaining poor condition segments across all groups. Long-term, years 5+, we shift toward a preventive maintenance strategy, which allows the city to avoid costly future rehabilitation and maintain network performance at a much lower lifecycle cost. With this sequence, the network shows consistent LOS improvement across all roadway groups, achieving service level targets within the planning horizon. Conclusion and recommendations. To conclude, our asset management plan provides a transparent and defensible investment roadmap for the city. Even with limited engineering data, the LOS-based modeling framework proved effective for prioritizing work and aligning budget decisions with service outcomes. However, to strengthen future AMPs, we recommend collecting more detailed condition and inventory data, especially for cracking, drainage, and structural layers. Improving data quality and completeness, which will enhance reliability of CPS scoring and LOS assignment. Strengthening prioritization models through multi-year deterioration forecasting as new data becomes available. Adopting a multi-year lifecycle perspective to ensure funding stability and long-term cost efficiency. Enhancing financial forecasting to capture long-term impacts of deferred maintenance. And finally, updating the AMP iteratively so it evolves as data improves and new city priorities emerge. Overall, this plan gives the municipality a clear pathway to improve road performance, reduce risk, and optimize investment over the coming years.